Welcome to The Explainer. So I am absolutely thrilled to dive into a massive technological paradox with you today. We are living in this wild, futuristic tech landscape of 2026, surrounded by artificial intelligence, hyper-connected smart cities, and advanced robotics. Yet, the invisible engine powering almost all of this futuristic innovation is a programming language that's over 50 years old. Today, we're unpacking the enduring, unshakable role of the C programming language in modern systems programming.
Okay, here's a quick look at our roadmap for today's explainer. We're going to cover the unseen king of 2026, how it's secretly powering the AI revolution, its raw speed and efficiency, its battle in the low-level trenches, and then wrap up with MISRA-C safety and its enduring legacy. Let's get right to it.
Section 1. The Unseen King of 2026.
You know, it's so easy to assume that newer is always better in tech, right? But C totally defies that logic. Pretty much everything around us that isn't a shiny smartphone or laptop interface is secretly running on C. Our source material has this brilliant quote, "C is the Latin of programming languages." And honestly, that hits the nail on the head. You might not speak Latin every day to build a trendy web app, but it is the strict, absolute foundational bedrock of modern computing. Learning it gives you a much deeper understanding of how every single other language actually works beneath the surface.
And the sheer scale of C's dominance, it is literally staggering. Check out these numbers from recent academic research. A massive 75% of operating system kernel code, yeah, that includes Linux, Windows, and macOS, is written in C. On top of that, 80% of Internet of Things device firmware relies on it. I mean, from the tiny, resource-constrained bare metal microcontrollers in your microwave to the anti-lock brakes in your car, C is doing the heavy lifting behind the scenes. There's no bloated operating system here, just pure, hyper-efficient code.
Moving on to Section 2. Powering the AI revolution.
So, we hear all the time about modern languages driving AI and data science, but, well, that's really only half the story. Python gets all the glory, right? It acts like this super accessible steering wheel, letting developers write high-level logic with ease. But C is the actual engine under the hood. When it comes down to the grueling mathematical computations, the massive matrix multiplications, and the hardware acceleration needed for AI models, Python just hands that heavy workload straight down to low-level C.
The secret sauce of this partnership really comes down to performance, because without C-based libraries, we're talking NumPy, Pandas, SciPy, or C and CUDA code running directly on NVIDIA GPUs for large language models, Python would just be way too slow to handle modern AI workloads. C literally eliminates that latency bottleneck.
Which brings us to Section 3, raw speed and efficiency.
Let's actually look at the data on why C is the go-to when performance is absolutely non-negotiable. Check out these sorting algorithm execution speeds from recent academic benchmarks. C blasts through the task in just 12.3 milliseconds. To put that in perspective, it executes nearly twice as fast as Java and a whopping 20 times faster than Python. No way, right? But the reason is simple. C has zero hidden runtime overhead. There's no garbage collector suddenly pausing your program to clean up memory. When you write a loop in C, you know exactly what the machine is doing.
And it's not just about speed. C uses roughly 3 times less memory than Python for identical tasks. Because C forces you into manual memory management. You explicitly allocate and free memory with commands like malloc and free. It runs incredibly lean. That makes it the absolute perfect lightweight fit for those constrained embedded systems where every single byte counts.
All of these features combine to make C a profoundly trustworthy engine. You get direct memory access, no hidden runtime bloat, and minimal resource usage. But the real kicker here, predictable, deterministic execution times. Think about real-time processing, like high-frequency trading, where a microsecond delay costs millions of dollars, or aerospace systems, where a delay means literal disaster. You need to know exactly how long an operation is going to take. C actually gives you that guarantee.
All right, Section 4, competing in the trenches.
So how does C hold up against its closest siblings and modern rivals in the low-level programming world? It's kind of this perfect Goldilocks scenario. If we drop down to the absolute lowest level, assembly language, sure, you get unmatched, cycle-accurate control over the hardware, but assembly is notoriously cryptic, super error-prone, and entirely non-portable. C sits right in that sweet spot. It gives you readability and concise control flow while still mapping incredibly closely to the actual machine instructions.
And what's super clever is how engineers get the best of both worlds with what's called the hybrid approach. In embedded systems, they use C as the baseline for core logic and device drivers because, well, it's portable and you can actually read it. But then, they'll inject these tiny inline assembly snippets exclusively for highly specific performance-critical interloops or real-time interrupts, basically right where every single clock cycle is a matter of life and death.
Now, if we move a step up the abstraction ladder, you might wonder, why not just use C++? Well, in strict embedded environments, C is still preferred over C++ because of its procedural simplicity. C++ brings in this complex, object-oriented overhead, virtual functions, and dynamic memory allocation, and all of that can lead to memory bloat and unpredictable execution times. And as we just talked about, unpredictability is a total deal-breaker in resource-constrained embedded systems.
Okay, but what about the shiny new modern challengers, like Rust? Look, Rust is amazing. It offers memory safety without garbage collection thanks to its borrow checker. But even against Rust, C firmly holds its ground. Why? Legacy. The embedded hardware ecosystem is massively legacy-driven. Microcontroller vendors still basically develop their hardware abstraction layers, their HALs, exclusively for C. So while integrating Rust is definitely possible, right now it's a gradual evolution rather than an overnight takeover.
Moving on to Section 5, Safety First with MISRA-C.
We've talked a lot about C's immense power, but we really have to address the elephant in the room. If C is so incredible, why is it universally considered so dangerous? Well, the hard truth is that C gives you unparalleled power, but absolutely zero safety net. Because of that manual memory management we discussed, inexperienced programmers can very easily trigger buffer overflows, memory leaks, segmentation faults, or write technically legal syntax that just results in undefined behavior. The source material uses a great analogy here. Standard ISO-C is like a high-performance sports car, but with very, very questionable brakes.
Enter MISRA-C. Think of these as the seatbelts and airbags for our sports car. Created back in 1998 by the Motor Industry Software Reliability Association, MISRA-C provides a strict, workable, and much safer subset of the C language. It lays out 127 rigid guidelines, 93 of which are mandatory, designed specifically to help developers avoid the darkest, most dangerous corners of standard C.
And the industry has adapted to this remarkably well. As noted by RMB Consulting, when you put C in the hands of experienced engineers who conduct rigorous code reviews and use static analysis tools to verify compliance, those vulnerabilities get successfully tamed. This strict, disciplined adherence is exactly what allows C to safely run life-critical systems today, from medical devices to the self-driving features in your car.
Finally, Section 6, an enduring programming legacy. As we wrap up this explainer, let's summarize the true value proposition of C as we navigate 2026 and beyond. Mastering C is about way more than just learning to program microcontrollers. It is literally the ultimate gateway to understanding how computers actually work at a fundamental level. It forces you to get your hands dirty with the stack, the heap, and pointers. I mean, it heavily influenced the syntax of C++, Java, and Python. Learning C fundamentally makes you a better, more disciplined programmer in every other language because it completely pulls back the curtain on the machine.
So I want to leave you with this thought. As our technology scales further into the mind-bending complexities of AI and the massive interconnected web of the Internet of Things, could it be that our most advanced future will always rely on our oldest, most efficient digital engine? Looking at the data, the evidence certainly points to yes. Over 50 years later, C remains the undisputed, unseen king of our modern technological landscape. Thanks so much for joining me on this explainer, and keep learning.